rigid body mechanics. It's about rotational mechanics. And the guiding questions are as such. How can we understand the linear motion be applied to rotational motion? So all the formulas that we use for linear motion can also be applied with a bit of a twist to rotational motion. Second thing is we can use torques to basically predict what's going to happen to the rotational motion. And how does the distribution of mass within a body affect its rotational motion? This is the last thing that we'll be looking at. So the first thing is about torque. Now, tau stands for torque, is basically the force that's applied times by the distance from the pivot times by the sine of the angle. Most of the times that we look at this, the angle will be 90 degrees, so we can ignore the sine theta. So it's tau is equal to F times R. This is the turning effect. The bigger the force, or the bigger the distance from the pivot, the easier it is to turn something. So it's fairly straightforward, I think. Okay, we have a number of formulas. They're going to look fairly familiar in a weird kind of sense. Like the first one is one that we've just looked at. This one is the angle. We've seen it's the distance is the average velocity times by time. Remember, V is equal to U plus AT, but instead of velocity we have rotational velocity or angular velocity. And A is not acceleration, it's angular acceleration, and so on. All of these are very comparable to what we've seen with Suvat equations, so it's going to be fairly straightforward. There's this thing called the moment of inertia, which is depends on the mass and the distance away from the pivot that that object is. Tau is the torque that we've looked at already, force times distance, is equal to the moment of inertia times by the angular acceleration, and so on. L is the momentum, is equal to the, basically, you remember momentum is mass times by velocity. This angular momentum is the moment of inertia, which is kind of the mass, times by the angular velocity, and so on. So all of these are going to be weirdly familiar, but not quite. Anyway, during this topic, we're going to be looking at all these aspects, and as we go through, we will tick off each of these points as we go through. So, let's say we've got normally we have a force applied to a cat. For example, the force goes through the middle of the cat, and then we have a translational motion. But this one is about rotational motion. So what would happen to an object if we didn't push on it along its centre of mass, but pushed along the side? If we pushed to the left or to the right? Well, this one would spin to the left, this one would spin to the right. Of course, it would go downwards, it would accelerate downwards because there's an unbalanced force downwards, but it's going to cause it to spin if it's not along the centre of mass. And that's what this topic is about. So, a torque is a force that's applied at an object at a distance r from the pivot point. There's the cat, yes. If he's been pushed there, fine, it will just be pushed downwards. If we apply it away from the pivot point, it's going to rotate round. So the torque can be calculated using the magnitude of the force along the line of action and the distance from the pivot point. Here's an example. The force is acting downwards on the left, and there's going to be a anti-clockwise torque, which is the distance r from the pivot point. So tau, which is the torque, is equal to Fr sine theta. In this case, sine theta is equal to 1. Now, the net torque will result in causing the object to rotate in a clockwise or counterclockwise direction unless it's balanced. So let's look at this one here, this example. Let's calculate the weight of the beam of a balance, which is balanced in this picture. So we have to basically show that since it's balanced, the clockwise torque will be equal to the anti-clockwise torque. So we need to calculate each one and equate them. So the solution is the anti-clockwise torque. Let's say we're applying 10 newtons, 3 meters from the pivot, which is here. Here's the pivot. So it's going to be 10 times 3, which is 30 Newton meters. The clockwise torque is equal to the weight of this body, which is, we don't know the weight, but we know that the center of mass of this bar is 1 meter away from the pivot. So we know that these are balanced. Since it's balanced, the two rotations must be equal in magnitude, so Fg is equal to 30 newtons. So that's the downwards force. So in other words, the object weighs 30 newtons, or the mass is around 3 kilograms. Let's look at another example here. The net torque will result in causing the object to rotate in a clockwise or counterclockwise direction. So here example. Calculate the length L there between the 40 Newton weight and the pivot needed to balance the beam as shown in the image. So here again it's balanced, so the torques, the clockwise and anti-clockwise torques, are going to be equal. So the solution is clockwise, we have 10 newtons times by 2 meters, because we're told that it's 2 meters from the pivot point. Also clockwise, we have 40 newtons times by L. So we have 10 times 2 plus 40 times L, which is 20 plus 40L. This is going to be balanced by the anti-clockwise torque, which is going to be 3 times by 100, which will be 300. And we know that they must be equal. So that gives the value L is equal to 7 meters. So now we've done rotational dynamics, we've looked at torque.